Poolside is really, really unusual in how much you guys release in the open. We hear about kind of open source models, and quite often all you get is kind of the weights and maybe like a few benchmarks, maybe a tech report, but you guys do way, way more. Hi, everyone. I'm Peter from Arena, and today we have a very exciting conversation with two researchers from Poolside AI who are going to talk about some interesting work they've done on the Laguna model and more broadly about how they train their models. So first of all, let's start with the introductions. Connor, why don't you start?
Sure thing. My name's Connor. I work on the evals team at Poolside. I'm our tech lead. I focus on pretty much everything agentic, but I work across the stack. My primary focuses tend to be on how do we take these different evals, make them reliable, repeatable, scale them out to running hundreds, thousands of times, and make sure that the signal we're getting is meaningful.
Hi, I'm Aalhad, or Al, and I also work on the evals team. I was a team lead for about a year and a half, so covering evals across pre-training, post-training. And lately, I've been working on an exploratory project around agent behavior understanding and trying to get more signal beyond what the numbers give us around how these agents actually do what they do and how they behave.
I'm kind of curious maybe for us as well to understand what kind of things do you release? What kind of things do you maybe go beyond what we just normally get, like the weights?
Pretty much as we can. So, of course, we have our open weight models. We've released a tech report with our first Laguna M.1 and S.2 releases that covers basically our entire process, our model factory. And with that, our evals, a bunch of the modifications we've had to make to evals because they don't really stay stable over long periods of time. And especially with the latest release, the trajectories that went into the scores. So if anyone wants to go audit them, see what our model is doing, see what we did, it's all out there.
Yeah, I think the trajectory publishing was like really important to us because I think one thing we were kind of surprised by is as an industry, how like we share benchmark numbers a lot, but we're pretty uncurious about what's behind the scenes. Like, what is the setup? What are the agents actually doing? Like, why did the next version score 10% higher? Like, what did it do materially differently? So we thought our trajectories would be a good place to start.
Yeah, I think the trajectory for me is particularly the thing that is particularly different. And I think that really points to what you guys are all about. So what I'm interested in is to get in your overall perspective of like, how do we train these kind of frontier models? How do we get to much better models being actually produced? Going back maybe a couple of years ago when you first started training these models to now, like what is exactly driving these models? Is it like just more compute? Is it, I don't know, reinventing some new technologies, or what kind of things really stand out for you?
That's a fun one. So I've been in the space for a little while. The first project I worked on was Copilot, so like the original code completions, right? And if like we want to go back that far to like GPT-3, GPT 3.5 Turbo era, those models had no thinking capability. They had no tool calls. Tool calls weren't a thing, and a lot of what was novel at the time was like ChatGPT and just using the model to predict the next number of tokens of code, right? And that was cool. But then, we saw multiple improvements over time. And then we started getting into more chat interactions. How do you have a conversation with a model about the code you're working on? Pro con the decisions, use context within your code base, context lengths started getting longer. The models started to have this like, new capabilities of maybe it can call, some kind of function that it can use. Then, tool calling became more of a thing. And then, then thinking was like massive because now, okay, models can reason about what they're doing and not just, completely give out, the answer right away. And then, right, not long after that, we saw, agents really start to emerge. About this time last year, a bit before that. I mean, agents kind of started to emerge, but took a little while to catch on. And now the game is how long can an agent go without a human interacting with it? How much can it do on its own? And, set up a loop and have it on its own, figure out what needs to be done and decide what complete looks like. So I think like throughout all of that, it's not just one piece that led to this. It's a bunch of like iterative improvements, a bunch of small new capabilities, and seeing just how far the same model could be pushed. And then like, how do you keep getting the human, further and further back from the keyboard?
And as far as your question about like what changed in terms of the training, like it's a little reductive, but to like kind of in some ways like everything, right? The kind of data that we're training these models with fundamentally had to change when we went agentic. the way we measure, what we measure on, all of that stuff changed. And I feel like from our vantage point, it's interesting because it's like a final model feels like the consequence of like 1,000 decisions, like 1,000 experiments that you're making, and it's a synthesis of that. And I think as capabilities evolve, those decisions get more complex, right? It's not just a model anymore. It's a harness. It's what tools are used in the harness and all of that working in concert. So I guess all of that has impacts on training.
Yeah, which is very interesting because a lot of the time what we hear is like, oh, this company had a lot more compute or something like that. Or I don't know, maybe they have a good RL pipeline, but it sounds like that's probably way too simplistic. So I'm interested, you mentioned you run a lot of experiments, and that's a kind of thing that I heard you guys talk about, run maybe tens of thousands of experiments. I really like to dig in. Like, what do you mean by an experiment? Or like when you say tens of thousands of experiments, like what do you actually do? Like what kind of things do you experiment on?
Yeah, so this is, I think, slightly related to the compute question as well, right? Because if we extend that analogy of like these 1,000 different decisions where you have a choice between A and B, in theory, if you can break down all of these decisions, you could just throw compute at it and basically ablate over all of these various parameters. But in the real world, like, that assumes like perfect eval signal. So you have a conclusive answer for each experiment, or like each decision point, and you can actually break down these things into these very, very individual, and you can imagine the complexity of that. That's too much. So I think that's where like an experiment to us is really anything where we have some decision that can impact the model. And we need some sort of, scientific evidence-backed way to answer, should we go with A or B? On the training level, this can be anything from like data mixes to the model architecture. But oftentimes they're also like more subtle than that. It's what subset of this eval should we even be looking at that gives us the highest value? Or in this harness, what is the way we should treat, I don't know, like parallel tool calls? All of these really are experiments because, they're all working in concert. Even this idea of training with like harness aware training is relatively new because we realize that, all of these things work in concert. So we have to experiment on how they work together.
When I think about training the model, it sounds like, at least kind of naively, then there's a big new training run. And I don't know, I imagine there's like a lot of data goes in, everyone gathers around, and there's like someone clicks a button and it kind of goes off. So kind of when you think about the experiments from your side, is it in preparation for the big training run, or is it actually much more kind of managed throughout the training run?
We do have big pre-train runs, right? For example, we have one going now, and it eats up a ton of our GPUs, and it kind of constrains what you can do. But then once that's done, we're going to have a bunch of experiments that then fan out from like the SFT stage, testing different RL mixes, testing all sorts of different things to try and get signal on what's actually moving the model forward. So it's a bunch of these like little decisions. And then we basically, at one point, we'll draw a line in the sand and say, all right, bring them all together. And that's what ends up making the final model. So like, kind of it's in preparation for it, but we're always experimenting and we're always trying new things.
Example for that too, like I think to answer that, like, is it one big experiment that you click off versus like iterative, right? I feel like in a perfect world where you could define all of the things you could possibly do, then you can just define those experiments up front. But what really happens is throughout, especially on the post-training side, like you start to see things that you didn't expect emerge. A very classic example is reward hacking, where it's impossible to kind of like upfront know all of the way the models might reward hack and then close all of those out. Like that would be prohibitively expensive. And that's just not really, I think especially the post-training process is a lot more iterative than that right now, to where you kind of have to get in, look at, and it forces you, with all the computer in the world, you may not have to do this, but it's actually kind of nice because it forces you to look at the data as it's happening and kind of like almost learn your model as it grows and see, oh, wow, okay, now it's found this new really clever way of cheating. We need to address that. Or, like, wow, it's really blown up thinking in this way. It kind of works sometimes. It doesn't work other times. So here's this problem in our data that we need to maybe address.
The whole evaluation, the whole kind of reward hacking, I guess, is a special case of that. Sounds like if you don't have good evals, you might as well give up, right? It's like if you don't know what you are heading towards, how could you know that you're even succeeding? So I'd love to hear a bit more. So when you are doing these experiments or when you're doing the training run, like how do you think about evaluation? What kind of things do you care about?
there's a lot that we care about. Of course, we want to see our number on the leaderboard. You want the final score to look good, all of that. But that's really only like the tip of the iceberg. And quite frankly, scores are very misleading. And we see this like in public releases of big models. Sometimes, it'll come out, it'll have amazing benchmarks, and then it'll just feel bad. So we have a lot of secondary metrics that we try to look into, and a lot of like really we try to treat. I think Al, you're the one that like coined this, but like an insights pipeline, right? Of like the evals give you a ton of data, these long trajectories, especially lately. We're onboarding benchmarks that are long horizon. You can't, as a human, sit there and, if you really want to, you can, but none of us want to sit and read a 24-hour long trajectory. So instead, you have agents review it. You have all these different derivative metrics that are trying to pull out interesting pieces of information to, help you hone in on like what makes this special, what makes it good, or what's making it bad, or even more interestingly, like this looks good, but here's why it's actually bad. The model, for example, like reward hacking is the easiest one to go back to, but there's so many different ways where models can technically solve the problem the right way, but produce a terrible result. And we've seen benchmarks come out for this that are trying to like analyze some of the like human taste aspects of it. Would a human accept this, or does it just look AI generate?
We learned this lesson the hard way a little bit as well, where our last year series of models, at the time, SWE-bench verified was like very much in the vogue in the SWE-bench family. And in many ways, like I think, especially at the time, like as the working with the post-training leads and to figure out what are the benchmarks, there's like a mix of practicality and signal, right? On some level, you have to get really, really comfortable with the fact that these are imperfect proxies for performance. You have to, because otherwise you'll spend all day trying to figure out the perfect benchmark, which doesn't exist. But you will optimize for the things that you implicitly as an organization kind of tend to prioritize, right? Like in subtle ways, like what benchmark scores are being kind of shared and stuff. Initially, SWE-bench verified when that was like our kind of like main hill climbing eval. We saw that it generated a model that was quite good at well-scoped kind of in repo coding tasks, but struggled a little bit with what modern agents needed, which is why we had to kind of rethink what are our hill climbing benchmarks. And, it's a constant process of evolving, like what are those signals that we look at? And you have to get really comfortable with throwing certain stuff away as it gets saturated and bringing in other signal. Like we had to do this time, like incorporating deep SWE, for example, because you will ultimately end up optimizing for what you choose. And you got to keep that moving.
One of the other fun things with that, older benchmarks, like SWE-bench verified, SWE-bench multilingual, even like around that era, don't really scale to the way agents behave today, because now all that data is on the internet. Agents can access the internet, and it's made its way into pre-training and like all of this. And so you really need to get far more sophisticated about how these benchmarks are run too.
That's a great point. And I think I'd love to maybe dig into maybe one example. I don't know, what's a good unit of work. And what I want to learn about is like in practice, when you are, I don't know, maybe doing one round of iteration or something like that, and then you have a model that is being trained, like how many evals are you kind of monitoring at the same time? When you're monitoring the traces, do you have like the same model kind of monitoring itself? Do you have another model monitoring? Like, talk me through kind of the details of that, because I want to really imagine what it looks like from your perspective.
Connor, maybe you want to talk about the benchmarking stack, and I can maybe take a little bit of the post-hoc analysis part.
Yeah.
This is very near and dear to our hearts, so excited to get into it.
And we just got out of a loop of doing it, and we're kind of in a build it, make it all, or like improve it all from our learning stage right now. So it's all fresh. So yeah, during the pre-training stage, like, because we kind of break it down, right? We have pre-training, we have mid-training, post-training, like SFT kind of stage, and of course RL, and then like experiments beyond that. But like, and of course quantization at the very, very end. But in the pre-training stage, we're running tons of benchmarks. These benchmarks are, of course, like all like next token prediction, and there's no chat templating, there's no agents out of the box unless you do some special work on top of it. But these are like basically to make sure our pre-training is going in the right direction, doing the things that at smaller scales it showed that it would do. And we're also using them as like regression monitoring. I mean, we have so many jokes internally about different people being our alerting, because we're just all glued to it at all times. We're all watching it. And then once it actually gets out of pre-training though, then it opens up. that's when we can start doing, your chat style benchmarks, your tool calling benchmarks, things that people actually like really understand intuitively better, and then your agentic benchmarks as well. I mean, we have to be selective, right? Because we only have so much compute. And so we've internally like honed in on a number of like kind of North Star benchmarks. And these are based off of like, what are we optimizing for at the moment? And we kind of cull other benchmarks based off of like what correlates with what. So we've got a couple of like different tool calling benchmarks, like Berkeley function calling, for example, just to make sure that that still remains functional and like that it's basically a regression check. Then we've got your typical agentic benchmarks like SWE-bench verified. Actually, we don't run all of SWE-bench verified anymore. We've taken a number of these like SWE-bench family tasks and made an internal benchmark that is basically the interesting pieces and the non-saturated pieces of many of this family that we call sweep. So we have sweep, we have then terminal bench 2.1 right now and terminal bench 3 because they're quite separate. And then now we're starting to onboard a lot more of these like auto research, auto experimentation, long horizon style tasks like auto lab, program bench, these different like benchmarks that you kind of set it and leave it alone for a while. At our current scale, when we're in our like experiment heavy phase where we've got multiple candidate post-training models and everything, we're running about 250,000 tasks a day. And so that is way too many tasks to manually review. It's also way too many tasks to send off for manual review if you wanted to like, pay data annotators. So we leverage a lot of agentic tooling for that. And Al, I think that's your that's your domain.
No, it's getting, I would say we're very early on this process, right? Like the first phase of it, I think probably, we do and a lot of people do as well, is kind of agentic judges and secondary metrics beyond just pass rate that are kind of like LLM guided. And we use those quite heavily. And those traditionally used to be like one-shot inference judges to pick up on things you might not be seeing through scores. Actually, one thing when Connor described that kind of pipeline of training, right? The scrutiny you apply to like what you're looking at kind of changes over time. So I feel like in many ways, like training a model to me kind of feels like really kind of like how we learn through school, where it's like pre-training, it'd be, if you wanted to like, raise somebody to be a really good software engineer, you probably wouldn't throw a battery of like software engineering interviews at them in elementary school, right? You kind of want to take a broad approach and just throw as many skills as possible and assess as many skills as possible generally to build that general intelligence. And that's kind of what pre-training looks like, to where you're looking at aggregate patterns and kind of aggregate failures, not so much like on a per sample basis. As you get to more kind of like post-training and RL, which in our analogy might be like college or even like preparing for a job, that's when it really, really starts to matter, because now you're looking at not just like the individual capabilities like math or English or like natural language, you're looking at how they work together in concert. And this is where, to Connor's point, like 250,000 tasks and all of them having like trajectories of like 50 to 100 or even more steps, right? Where we started with this kind of analysis was to answer simple questions like, why does candidate A score better than candidate B on terminal bench like 10 plus percentage? For pre-training, you can ablate like so many things that you don't necessarily have to have an exact answer. You let the experimentation tell you. But in like agentic and post-training world, you kind of like to guide where you want to improve your data or your RL pipeline. You need to have an answer to these kind of like fuzzy questions. And so we started, like everybody else, with using kind of like just agents throwing it at this problem, like, hey, analyze this massive data set and help draw conclusions. That is super time expensive and compute expensive, because you're using this very heavy hammer of maybe the best model you have available to, in a very unharnessed, unguided way, just like give me what I need, right? That's of course supplemented with actually like we have quite nice tooling for looking through trajectories individually, but then you have sampling bias where you probably might look at the tasks that you're most familiar with, because these tasks are super hard. So even familiarizing yourself takes time. So now we're kind of exploring, internal tooling that lets you kind of combine these AI agents with humans to kind of provide a high level analysis goal, some sort of harnessing and methodology so that, you can assure that each sample is reviewed and you get findings in a more like evidence annotated way. So if there's a conclusion like, hey, model A is better than model B because it tends to take more time in exploration, you can have evidence that are annotated in trajectories to actually give you confidence that that finding is true. And the ideal kind of loop there is you can take some of these findings and then correlate those. So like, okay, can I find examples of this in SFT? Or does this give me some hint as to which like RL reward maybe needs to be modified? But I would say we're very, very early in that process. So more like on the, first we're working on building tooling to let everybody do this a little easier. And from this, gain patterns so that we can build more of like an opinionated, kind of auto review system.
Yeah, I think it sounds incredible how much data is getting generated and how much actual work there is to kind of dig through it. And I guess one thing I'm curious about is, I don't know if you kind of thought about it this way, but how much compute or effort or whatever is the right metric is spent on like the different stages, such as, for example, pre-training, post-training, I guess the one that people typically think about. And there was kind of discussions of like, oh, is RL now half of like 50-50 split? But it sounds like so much effort is actually going into that kind of active review and evaluation and benchmarking. So do you have any sense of like how much is going into each part of your training pipeline?
I don't know if we can quite speak to like kind of exact numbers or proportions, but as a generality, I can say that as you get later in the stages, you start to go from like less training time compute to like proportionally to more like test time compute and eval compute. So like you kind of see this like pre-training compared to post-training. Like I don't know if this is helpful, but we can't speak to exact numbers, but you start to see a lot more transfer to like real test time compute when it comes to like RL and post-training.
Yeah, and I guess maybe to maybe ask the question differently as well. Is it like sounds like the trajectory is that you need more and more compute, maybe better methods, or like that sounds like the area where you see the trend is going up, right? In terms of train or kind of spending computer resources, whatever exact form it takes. It sounds like that's what you're kind of thinking about. How do you kind of increase that, make that more effective? Is that right?
Yeah, it's like two trends kind of like maybe countering. Like one trend is wanting to diversify your tasks, ultimately downstream like RL tasks, right? Or even, let's say, post-training data that's more agentic, and agentic data tends to be like just bigger and require more compute, right? With also making RL more efficient to kind of, use the compute you have more efficiently. And I feel like those are two kind of like parallel tracks that are going on right now.
There's some like competing things too of like, how do you make sure the model can explore for a long period of time and do these difficult long horizon tasks where like build me an entire app that mirrors Slack, for example, like feature complete, make no mistakes. But then there's also the, hey, I just need this quick atomic thing, go into this file, fix this bug, let me know when it's done. We have a good mixture of tasks that'll be like 20 steps maybe in the trajectory at most. And then there's the opposite end, which is set no limit, let the model decide when it's done. If it takes 24 hours, it takes 24 hours.
And this is where like human constraints come into. Like you could let the model RL like even longer, and maybe there's like even more gains. But that's where it's like one of those things where do you bake this thing to perfection, or do you kind of focus on the next iteration of improvements? And that's like probably not well suited to answer that, but that's like a very, very human organizational decision.
I'd like to dig into that more. So in terms of the long horizon tasks, that also sounds like the big change that you guys are seeing in terms of maybe a couple of years ago, it was all kind of very chat maybe based, and now you've got these super long agentic tasks. So how could you possibly evaluate, the task that goes on for 24, 48 hours? Like how do you think about that?
We're still figuring it out, but it's very difficult because there's a couple of things. One is like you've got to get the fundamentals right. Your evaluation system's fundamentals must be rock solid. That means, high reproducibility, low infrastructure failure rate, good detection for things like reward hacking and new emergent behaviors, and then good interpretability tooling. Because without all of these things, you won't actually know what's going on. So if I were to pull like, let's say AutoLab, for example, because I find this sort of benchmark very interesting. Broadly speaking, the model is optimizing something and then using a validator to check its work. So that validator is for like a separate environment, basically. Model can send its work over, have it checked, get the result back. That way it can't just cheat and read, the validation. This is really interesting though, because you're not just looking at a score, right? You're looking at optimization over time. And so this kind of changes the way we've thought about a lot of benchmarks. If you think about like your SWE-bench family, go in, fix bug, done. Clearly verifiable, unit tests, easy software engineering problem. But now we're opening it up a lot more. And when this happens, things break in very, very weird ways. The model can make a very poor decision about how to optimize something, eat up all the RAM in the sandbox and crash it. Well, you need to know that happened, and you need to be able to tell that's what happened. So we've spent a ton of time in preparation for these sorts of tasks, nailing our fundamentals, building out our observability stack, and like really, really trying to hone in on when we have these runs and we get these signals, how do we know that it's legit? And then on the like signal side as well, I think that even as an industry, we're still kind of figuring this out, because you look at something like Program Bench, where the model basically has to reproduce an entire repo from a binary. I think the best on the leaderboard of absolute pass rate right now out of 200 tasks is a 0.5%, so fully passing one. And instead, we're looking at things like partial pass rate. Like partial pass rate is very hard to interpret. And so you almost want to know like, feature completeness or like functional usage parity and like these more fuzzy things. So these are some of the other verification methods we're starting to kind of explore.
I would say the infra noise is not anything to like kind of like shoo away either. Like we as an industry found out like how much infra noise, like I think Anthropic has published on this, right? Connor has a nice little like Oracle. So we basically do daily Oracle runs on all our benchmarks to just say, if you pass the golden solution, how many times do you actually get the expected 100% score? And that turns out to be deceptively complicated, because cloning the benchmark and running it individually one time might work. Running it at scale across like dozens of checkpoints has like for example, Terminal Bench has all of these dependencies on third-party APIs that might get rate limited, that now all of this stuff causes noise where you might be making an imperfect training decision based on the fact that a third-party API was down. And that like has a lot of consequences downstream. Just getting those details right is, for long context, like all of these problems get exasperated for long horizon.
Yeah, this is a screenshot from one of our dashboards from when we were doing a deep dive into this exact problem. So each dot on here is the percentage failure of the Oracle, which is like the golden patch. In cases where it's empty, it was either it didn't fail at all, or we didn't have it implemented yet. So you can see some outliers. Like we had a bug in Tau 3 for a little while. Reforge, one of my pet projects, started acting up. But what's been killing us is in Terminal Bench 2, we had a number of issues where like one was our implementation of our sandboxing didn't allow for spikes in RAM. And so if it hit the requested amount of RAM, the sandbox was killed. Then after looking into it, the official implementation actually allows for spikes because of this exact issue. You can't guarantee how much memory will be used at all times. But the one that Al just mentioned was really painful, and it's something that we've had to change in SWE-bench verified and SWE-bench multilingual and multi-SWE-bench. Actually, the one that was really painful for us was actually Java programming tasks. So a lot of these benchmarks, you don't build the image with like everything preloaded. So for example, if either the task requires installing a new dependency, or if the build for the repo hasn't been done yet, and so there's no like cache dependencies in the image, it has to go out to the internet, download those dependencies, and run. Well, if we're running this thousands and thousands of times a day, Maven really doesn't like you to do that. And they want you to have a proper cache within your network so you don't constantly ping their servers. And so Sweep, our composite benchmark that has a bunch of these different multilingual families, you can see we were like, this is the Oracle. This is applying just the golden solution and running the validation. We were bouncing around between like, what is this, 6 and 13 or so % failures every day, just like purely from noise. And then we got a cache, and we got the cache in network, and we went down to 2%. Cache was missing a few things. But we have to keep making these iterative improvements because it's It's one thing if a benchmark works once. It's one thing if it worked when you pulled it and wanted to explore it, cool. But that just isn't the scale we run at. Like model labs, we've got to run these things constantly.
And 6% is huge. That's like the difference on a leaderboard between a tier 1 model often and a tier 2 model as we perceive it. There's one more kind of long horizon. Sorry, I know we've deep dived on this a little bit. That's more like strategic for us in the industry, which is long kind of horizon benchmarks measure the ability to kind of go off and independently work on a task for a very, very long time, right? But I think that's only a subset of kind of engineering. There's also other aspects like collaborative intelligence and how well it can actually recognize that, hey, I should maybe pause here and bring in information to make this more efficient. And I think that really gets left on the table. And we kind of see this with current like state-of-the-art models as well, which can do these insane math problems, but sometimes feel a little frustrating to work with. That's a real concern that we don't really know how to tackle, which is in real software engineering, right? Like, how do you, like, for very task completion focused models, how do you prevent this kind of rabbit holing and wasting of compute or wasting of time because the model is so, hell-bent on going as long as it can to, work its way out of what might be an impossible problem?
Actually, I had no idea, which I know you kind of say it, and it does make sense in terms of the level of infrastructure you need to deal with. Because even like as a user of the models, as I'm testing, I run into so many like random issues, and it's just kind of me using the models. And yeah, I can imagine running many thousands of experiments is a completely different ballgame. But I think you touched on something interesting in terms of like this kind of, we see sometimes models which like feel kind of quite benchmarks, and they're not maybe quite feel like there's something missing kind of in between the benchmarks. So I know you mentioned like you maybe don't know how to deal with all of it, but like do you like vibe check the models, or like how do you think about this?
Yeah, and internally, we're constantly deploying models to our internal like vibe check setup. We pretty much as soon as we have a promising model in like a usable state, ring the bell, summon everyone. It's time to vibe check. Like get on our harness, go try it. And then we've had historically over time like multiple different versions of trying to take those, turn them into benchmarks. But like the ultimate thing is just get your hands on the model and try and do your normal development work with it. It's always a challenge to get people like, no, put down your model of choice, go use this one, and like push it. Tell us what sucks. Help us find these rough edges. So we do a lot of that. Then the other thing that we're trying to do more is like build up like a repository of just like open-ended tasks that we can kind of A/B test, kind of like arena style of like how do we compare our model against another of our models or against another open source model or whatever, just kind of get that feel right, because it's such a tricky piece.
And I think like UX has like, it's like that, if there's friction to this process, like I as a developer who want to do my development, like any friction makes it like like that much harder to generate, kind of valuable dogfooding data or like vibe check data. So that's where like I'm very interested to see like what platforms like Arena do, because like really, really making it more frictionless to compare and like try things in a way that like this valuable kind of trajectory sets are generated, and we actually understand like what is the difference between like, let's say Opus and 5 GPT models. Right now, I would say it's a very like ad hoc kind of like we gather the troops kind of effort that we need to invest more in.
Yeah, that makes sense. And my very first use case for Arena was just to calibrate myself on like what do models feel like. So yeah, that feels like, and especially blinding myself to what model I'm using just helps me also like make sure that I stay unbiased. One thing I know you mentioned about and I know you guys wrote about this about long horizon tasks, is that reward hacking is that kind of issue that's starting to get more and more fame now and more attention. So, like, how much do you encounter it? Like, what kind of weird things do models do? Like, how do you catch it?
I mean, we catch it, I think, on a weekly basis. I mean, I don't know. It's one of those in RL. There's this balance, right? Of how do you put the model in an environment that is representative of what the end user will do, but not give away the answer. So for example, when I'm using a model locally, if it thinks the answer's on GitHub, and it is, I want it to go find it. I don't really care that much about it, like coming up with this, novel approach on its own. No. Go use a verified solution. That's what I want. Problem is, benchmarks don't want that. Training doesn't want that. And so, we run into cases where the model finds, let's say, a hole in our network policies, or one that we've published an article about was in SWE-bench Pro, for example. All of the images shipped with the solution still in the image because they're public open source repos. They basically take a commit, work backwards, make a solution or make a task from that commit. But that commit was still in the containers. And so like overnight, our model suddenly jumped like 20% or something crazy. It was like state of the art on this benchmark. And we're all like, all right, come on, what'd you do? And, it turned out what that version of the model in RL was like very eager to use Git history to understand the current state of a file. Because like it had just kind of, again, anthropomorphizing a little, but figured out by knowing the chronology of this file, I can better understand the state and where it needs to go. So then it logs the history and sees, oh, there's all these future commits. I'm going to go look at them. And then found that, yeah, that was in there. And like, just on that benchmark, absolutely crushed it. And so then we had to go in, scrub all the images, check other, like then this starts this whole exploration of, oh no, how many others have this problem? But, that's what it is today. Or not today, what it was a few months ago. Today, it's, finding holes in networks to try and download packages. For example, we've had issues in SWE-bench family tasks of the model just realizing, oh, I'm in Django. Let me just download the latest version of Django and compare. And then finding out that it's in an old version and can mine the solution. But then we're starting to see in Frontier Labs even more like all the articles lately about Opus and all these other models like breaking out and doing nefarious things. Those are interesting. Those kind of blend the boundaries between what is reward hacking and what is outright misalignment.
This is kind of a whack-a-mole problem, which is both like scary and exciting. Like we described that first stage where it exists in the Git, local, solution exists. What about something like Terminal Bench where, it's not from a source repo? Models get more and more clever about cheating because like the seed of that might exist in SFT and RL will make it very greedy to find the optimal way of solving the problem. So we've seen some pretty complex reward hacks evolve where even by cleaning up the local Git repo, even by blocking access to like raw GitHub, it will go as far as to like discover, like guess at what package it's operating in, downloading the source code of that package off of like some random mirror, and then doing a diff of that package source code against its own. So on one hand, it's like it's clearly an immersion capability, how like it's a sign of the intelligence these models have developed. So now some fun examples I'm happy to share as well of some of these things. But like our lesson for that is basically this has to be a continuous exploration exercise where we use that tool I mentioned earlier, as well as others, to sweep our eval, like literally go like do sample review on our evals to discover new reward hacking cases, and then apply those same kind of searches to our RL runs to see like where they emerge. But the biggest salve was honestly telling the problem, hey, a reference solution exists. Don't use it. To the model, it's not necessarily cheating, right? It's like, let me solve this problem efficiently. So we're still early innings on like, what is the right way to tackle it, but it is a whack-a-mole problem.
It actually sparked some interesting conversations of like, we had this prompt addendum in Laguna S2.1 of, hey, don't cheat. Here's what cheating is, looking on GitHub for the solution, trying to download the package that you're in, like these very specific cases that model was very eager to do. And it created some like discussion of like, why do you do this? Why do you have to like prompt the model not to cheat? It's like, well, let me give you an opposite example. In Terminal Bench 2, there was a case where the model had to go download a video from YouTube. YouTube has quite good bot detection. This is effectively a botnet going to download a video, like when you reduce it down to what it is at the scale we're running. And so do you want the model to just give up and say, oh no, YouTube said no? No, what it would do instead is it would try again and again, and then it would go, okay, let me try Internet Archive. And then Internet Archive like would sometimes allow it, sometimes not. And then in the cases where it wouldn't allow it, it'd be like, oh, but I know it was a speedrun video. It'd be like, oh, I'm going to go to like one of the speedrunning websites and see if I can find it there and download. I mean, the model was spending 100 to 200 steps just trying to figure out how to download the video in early stages. And that was like mind blowing to me because I was like, oh my God, like, wow, it's doing so well. And like, that's a good example of being very resourceful, being very clever, trying to figure out how to solve the task. But then it's also at least a good reward hacking capabilities of, no, I'm going to try and solve the task the way that I know it can be solved. Because unfortunately, for some of these old benchmarks, like SWE-bench verified, SWE-bench multilingual, the model's aware it's a benchmark. A lot of other labs have shown similar model awareness. And so we kind of just share like to it. No, don't do these things. Solve it on your own. And it works quite well.
Yeah, what's unclear from a research level is like, what is instruction following versus what is misalignment? There's certain public models which are actually, despite not being instructed to, almost never cheat. Other ones cheat very aggressively. And it's still open question whether like that is linked to like a general alignment or it's just a factor of, being over-optimized for task solving or something.
It is kind of interesting, where the line is, because in my personal work and experience, I do find sometimes that, you definitely want the models to be tenacious and just like figure it out. And like, I don't really care what you do, just go figure it out. Although I did have a model send an email to academics once. So it really took it in its stride to like do whatever it takes. It was missing some data and it was a bit overeager, which was a bit embarrassing. But in other cases, I definitely see the model to kind of hack into, well, no, hack maybe is a strong word, but like really interpret it so precisely to make my task work for that very special case, and then kind of disregard everything else. It's hard, probably you need a lot of judgment to know when it's like when you want the model to go crazy or when you don't. So it's kind of interesting. One thing you mentioned is like the model being aware of the fact that it's being tested. And I think Anthropic, OpenAI probably published it like years ago, right? That was a known thing. And I remember me reading like trajectory of my own testing. You definitely see this come up in the trajectory. It's like, am I being tested kind of thing. So like, what's your view on that? Do we have a serious problem here that the models just know and they kind of, adjust their behavior? Or do you think that's still reasonable to kind of carry on?
So I have a fun example of this actually. So this is a terminal bench run on a very popular model that from a public leaderboard and trajectories taken from like the Harbor kind of public trajectories. I recognize as a terminal bench GPT-2 code golf task, I'm fetching the source code. In other trajectories we've seen, we close down GitHub, we close down, like local Git access. You can't block internet outright because you want your model to be evaluated on tasks that require internet. There's no clean solution here. I think every benchmark will eventually, that's popular, make its way in some way to being accessible on the internet. So I think it's like a bit of a carrot and stick. You kind of instruct the model that a solution exists out there somewhere, but I want you to solve it from first principles and have these detectors, which penalize it when it copies a reference solution. I think that's a partial solve. I think more so we just, in benchmarking, just need to get more and more out of distribution tasks, which inevitable conclusion is we just need to get better at kind of more online evaluations, I think. The Terminal Bench folks released a really good write-up on how benchmarks should actually be constantly evolving and not like a static set of tasks. I think that's the only way we kind of stay ahead of this.
You know what it sounds like? It sounds like Arena, where we don't have static tasks. So yeah, I'm a big fan of this. I definitely see a challenge that even, without kind of anyone particularly doing anything bad, it just kind of slowly deteriorates as kind of models get wasted. So yeah, I definitely see that that being an issue.
Those are hard to use as training signal, I will say, because static benchmarks, like it gives you don't want noisy data when you're selecting between two checkpoints. And every model is like selecting between checkpoints on like a large scale. So I do think there is an argument for static benchmarks and, traditional benchmarks. I just don't think it's the whole picture.
Yeah, no, that's fine enough. I think if you kind of have to just measure like for like, whether like this one is better than this, then I definitely get it for sure. Actually, I want to ask you Like, can you think about the world of benchmarking, which is, very close to my heart? Like, do you wish you had some kind of benchmarks that you don't have? Or like, do you have any kind of wish list of the type of things the benchmarking industry should do better? I don't know. It doesn't quite feel like, we figured it out. So like, what's your view?
I'll take the second half of that first, of like what I wish everyone would do. I wish people would do like what we're starting to do as well. Like, that us publishing our trajectories, like, is us trying to do what we wish everyone else would do. A very convoluted way of saying that, but like, it's very hard when I look at, let's say a model is published and it's just, yep, we got these scores on these 3 benchmarks. Use us. It's like, okay, but like, tell me more. And because like when I look at these, this is all I do. So of course I want to know more, but it's what environment, what sandbox provider, for example, was it yours? Was it a public one, etc.? How were they provisioned? What was the size? What was the image? Like, how did you diverge? What framework did you run with? If you're using your own in-house framework, tell us some of the info about how it's running so it's somewhat reproducible. What's your harness? What's the harness setup? All these like pieces of information to reproduce the run, and then give us the trajectories too, because like that's really where the proof lies, and that's where you can hide a lot of things. Like Al said, we've seen it a couple of times where you go review like the trajectories on leaderboards and you just find things. And I'm sure, if people were to dig into our published trajectories, you'll find things too. I mean, like, it's just the nature of these models. There's more information than anyone can like single-handedly review. By making it public, we can help kind of review like as a community. And then your other question, I think, was like, what benchmark doesn't exist? What are benchmarks missing? There's this tension that I notice right now, which is like a lot of original agent benchmarks are like human vary in the loop, human hands on keyboard, directly interacting with the agent at all times. And then now we're trying to make this jump to like very long horizon. How do I set the model for 24 hours or longer and let it do its thing? There's a missing piece in the middle. To me. And we're starting to see these come out more and more, but like agentic, medium horizon, but multi-turn. So for example, like Tau 3 explores this agent or this idea of like a user agent. I want to see more there where it's like, how do we do agentic coding tasks or like good agentic long horizon tasks, but decompose them into a series of medium horizon tasks? Because realistically, that's how a lot of people are using the agents today. And that's like, we've been like reviewing a lot of user engagement, user feedback, and that's what we're finding is it's like the average trajectory is not as long as our like extremes and benchmarks. So, sure, we should be building for the future. We should also be optimizing for the way people are using it now, because we have a lot of power users right now as well. I talked to some of my friends who like aren't as into AI and aren't at companies that are letting them use AI, and they're like, wait, you do what? And so there's going to be this like harsh growth curve for a lot of people if they just try to go straight to long horizon. So I think I'd like to see that.
I'd echo Connor on both points. The first one, our personal soapbox is like publish more trajectories. And that's not just like even selfishly, right? If people find stuff in our trajectories, we want to know that. And in general, to understand how these things behave, I think we're starting to get to the point, and with very public examples of it no longer just becomes how did this task complete or not, or the what, but like the how and the why is starting to matter a lot more. And I think the only way we get there is just publish it. Let us understand, like let's all as an industry understand the thought patterns, the reasoning patterns, the kind of triggers towards certain misaligned things that happen by publishing more in the open. On the dream benchmark, I completely agree with Connor. I think there's like, I think collaborative intelligence is a capability that we don't really optimize for because it's hard technically. It's hard because it's hard to empirically kind of assign partial credit. It's hard to simulate this like variant user, interacting with it in these like different paths. How do you assign a credit? Like, how do you even score something like that? And I think replay is very hard. Like, I think a dream benchmark would be something like people contributing real work that they've done in this platform, which looks a lot like Arena, but also with the ability to replay it and be able to say, okay, like this is how this entire thing could have gone better. So you can actually compare a little bit more apples to apples. I think that'd be like a dream benchmark.
That's interesting. Maybe some homework for us to have a think about. One question maybe that I'd be curious to hear your kind of speculation on is, let's say that today open source models, they get much better, but there's still a bit of a gap. So let's say, I don't know, in an amount of time, you release a model that's as good as Fable or something like that. What is different? Like, did you get a lot more data? Is it like a lot more compute? Is it, I don't know, better benchmarking? I appreciate the answer is probably a bit of everything, but like, what's your senses like if you had to bet, like what was the real difference?
I mean, compute is a big factor, right? Like in some ways, it's like, I think our approach to things and why we believe so much in the model factory and Laguna S is that you kind of get the recipes, like you get the details right at smaller scales. Like you can experiment a little bit faster at smaller scales given like more fixed compute. And obviously there's scaling concerns as you scale up, but ideally a factory approach lets you scale up a little bit more. And ultimately, like we just know that more compute, more parameters, these things kind of establish almost like the size of the brain, like the capacity for what it can do. But then I think the details around post-training evals help you actually extract that capability in a much more like predictable, expected, and consistent manner. Right? Like I think like the benchmark analog might be like being able to solve a problem once in several tries versus consistently solving it in a very good way every time. And I think that's where, the ability to solve it, I think we know a lot of learning comes from pre-training and their scale, compute, the amount of data you have, the quality of data, all are like the biggest factors. But then the details really start to matter for the behavior aspect of what the model does with that intelligence.
And to give you an example as well of like why, because it's really easy for us to say like compute is what matters, right? But because like we're constricted on compute, everyone's talking about compute, trying to get more massive deals about it, all of that. But so when I first joined, we were going after a model that was roughly like Laguna small to Laguna, like maybe a little bigger if I remember right. And we were running into a lot of issues, and this was never released. It was purely a research project, right? And so we were running into a lot of issues though with that model, and then the subsequent Laguna M that we did release because it's so big and like relatively. And so running experiments takes time. And then we turned around and did Laguna Extra Small, right? And Laguna Extra Small came about while we were like we were in the run up to releasing Laguna Medium. And this was the first model we had internally that we were no longer constrained by compute because we could run it on one replica, one GPU. I remember the day like we started running post-training evals and agent evals on it, it blew up our stack because suddenly you could say, I'm going to run 64 replicas in parallel at once on this benchmark. And each replica could handle like 10 cases. You're like, oh, I can run the entire benchmark at once in one go, no sequencing. And then I'm also going to run it with multiple repeats. And so everything in the stack just started breaking in unique ways, which was fantastic for us though, because then we were able to make things faster, more reliable, more robust. And so theoretically, if we could run, let's say, a Fable-like model that way, the amount of experimentation, the amount of learning, the amount of everything across the stack that would be improved was just like unimaginable. It would just be everyone's dream, I think, because like you could do so much. But unfortunately, in the current paradigm, like, no, we cannot, like, no, it doesn't, we don't have that kind of compute.
Yeah, you have like more shots on goal to get things right with smaller models. And then when you're doing the training run, just because of the time it takes to train as well, that's what the value of, I think, Laguna XS was for us a lot. Like just the sheer amount of experiments we can do. And not all of them translate to as you scale up, but at least the details do start to translate. So I think that was like really valuable. And like compute is definitely a big factor, but it's not everything, I guess is like the summary, I would say.
One thing I kind of had it in my head, at the back of my head when I'm thinking about like the different model sizes, and maybe you can also share your view, is like there's probably a trade-off, right? You can have a ginormous model that maybe the first run and it's good, but then I wonder if you actually have a smaller model that you can have more iterations on. Like, do you actually end up getting more velocity? And it's like in that way, smaller model is better. Like, how do you think about that kind of model size?
Is that from a training perspective? Are you asking, where like you get more iterations?
Yeah, I'm guessing, especially in that kind of RL paradigm, right? As you kind of have to keep training it. Is there a reason why you choose like certain size model? Is it because you can then have more shots on goal and kind of keep iterating more, or is it like, oh, actually, you would have just had bigger model as much as you can handle?
For us, there was definitely an advantage in making smaller models. One is like there existed a gap, and so we could get a lot of usage, a lot of people engaging with the models, and there is an amount of information you just can't learn until users engage with the model, right? So setting that aside, everything goes faster with smaller models. Basically, it like Al said, not everything one to one scales up and translates, but it lets us do things like iterate on RL approaches, iterate on data mixes, iterate on okay, what does good, for example, multi-harness training data even look like? These very fundamental problems you can solve at a small scale faster, and then a lot of them will scale up better. And so it's better all across the stack. It's better for training, better for evals, better for the infra. I mean, if you are limited on compute, for example, and your network setup, like your egress and everything, turns out it doesn't scale perfectly. Well, you won't find that out only training a very few small massive models. But if you train tons and tons of tiny models very fast, it was like the entire company leveling up internally.
For your model factory, it's huge to exercise, because your model factory is not just about making a point in time best model, but it's about consistently training better and better models. And I think for their more iterations help. If you pigeonhole too much on capabilities, there's a chance that the larger size model just solves that capability just from being smarter. But I think in a lot of these other things like infra, I think every team probably has stories like this, but from our evals perspective, even just the insight that, hey, we need better analysis tooling post-hoc, and we need, we need to be able to monitor infra better. All of these learnings, I think, don't happen when you're waiting a month to see the final checkpoint, right?
And I think what you're talking about the factory, and I think here you talk about your whole process kind of end to end, from kind of pre-training to monitoring to RL iteration, makes me really bullish on what you guys building, because I think this idea of the model factory, the fact that you can run so many experiments and how quick you can get these models out the door and how many you train, I think sounds like you are already on that kind of path to just keep smashing it. So, which is amazing to see. So, thanks a lot for this conversation. I've enjoyed learning from you guys, but I want to give you a last chance to maybe share any kind of call to action or anything you want the audience to kind of take away.
I think mine would probably be, well, first of all, check out the models, try them, let us know, give us feedback, look at our trajectories. If you find interesting things, tell us. But also for other labs, other groups, work more in the open. We all learn when everyone works in the open, and it makes sure that we're all working towards frontier intelligence that will be better for everybody that way.
My call to action already mentioned, you don't have to publish everything, right? If there's concerns, I know there's big debate about distillation and things, but publish something so we all understand how these models work better and we can make better choices. And I think it's good competitively as well, just to say we're proud of how our model behaves. Go check it out. And I guess the other one, I'm really excited about the work Arena is doing, and really want to, I think we touched on that. The best data is just how are real people using these models, and where are they getting frustrated? Where are they really liking what the agent is doing? So, I guess making it easier for people to contribute to something like that, because I think that's really valuable, and making, maybe cool benchmarks and ways that we can analyze that data so that we all kind of get more sophisticated in how we use these agents would be really cool, I think.
Amazing. Love it. More models, more openness, learn together. Amazing. I learned a lot myself, and it's really good to hear from the actual practitioners in the field. Thanks a lot for joining and sharing your insights.